All right, today we're tackling a really big question in cosmology. Is that mysterious force that's speeding up our universe, dark energy, actually changing over time? Let's dive in.
So you've probably seen the headlines about this, right? Especially with some recent results from big surveys like the Dark Energy Spectroscopic Instrument, or DESI. And all this talk has stirred up a lot of excitement, but it's also created a bit of confusion about what the science is really telling us.
So, to cut through all that noise, we're going to focus on just one specific, recent, theoretical paper that digs into one of these possibilities. Now, we're not looking at new telescope data today. Instead, we're going to pick apart the mathematical framework of one proposed model to really understand what it can tell us, and just as importantly, what it can't.
So here's our game plan. We'll start with the big picture, the dark energy puzzle. Then we'll look at the new model these scientists built, see what it predicts, and, this is the most important part, we'll put it all in context so we can get a clear answer to our main question.
Okay, first up, the dark energy puzzle. Before we can understand this new paper, we have to get a handle on the mystery it's trying to solve. I mean, why are scientists even looking for alternatives to our best current theory of the universe in the first place?
Well, our standard model of the universe is called lambda CDM. That lambda part stands for the cosmological constant, and it represents dark energy as this constant, unchanging force. And look, this model is incredibly successful at explaining what we see, but it leaves some really deep questions unanswered.
You see, lambda CDM has a couple of major theoretical headaches. First, there's the fine-tuning problem. Our theories from particle physics predict that dark energy should be, well, astronomically bigger than what we actually measure. And second, there's the cosmic coincidence. Why is it that right now, after billions of years, dark energy and dark matter have a roughly similar influence on the universe? It's puzzles just like these that really push physicists to explore new ideas.
And that brings us right to Section 2, a new theoretical model. So, let's see how the researchers in this particular paper went about building their own alternative universe, right there on paper.
And this is maybe the most important point of the day, and it comes straight from the authors themselves. They state very clearly that this is a theoretical investigation. This is not an analysis of data from a telescope. They are building a mathematical what-if scenario to see if it holds together and to find out what it might predict.
So this model has two main ingredients. First, instead of using Einstein's general relativity, it uses something called Brans-Dicke theory. In this theory, the strength of gravity itself can actually change over time. And second, it uses a concept called ghost dark energy, or GDE. This is an idea from quantum physics that says dark energy is dynamic, not constant. And what's really interesting is that this GDE idea might offer a way to solve that fine-tuning problem we just talked about.
You can really think of building a model like this as following a recipe. The researchers start with the flat universe, which is what our best observations point to. Then they swap out standard gravity for their Brans-Dicke version. They add in their dynamic ghost dark energy, and then for the final step, they include a possible interaction between that dark energy and dark matter.
Okay, so that's the recipe. Now for the really exciting part. What does the model predict? What kind of universe do you get when you combine these ingredients and just run the numbers?
The first big prediction is all about the nature of dark energy itself. In this model, dark energy is not a constant. Its equation of state, which is basically a way to measure its pressure against its density, actually evolves over cosmic time. You could think of it as the pushiness of dark energy, and in this model, that pushiness changes.
And the model's behavior shifts over time. So in the cosmic past and in our present, it acts in a way that lines up really well with a lot of our current observations. But here's the twist. In the distant future, the model predicts that dark energy will weaken. This is the core theoretical idea that connects back to all those headlines about a changing dark energy.
Now, the second key prediction is even more dramatic. This model suggests that our universe goes through not one, but two huge phase transitions in the history of its expansion.
So here's what those two transitions look like. The first is one we've actually observed. A few billion years ago, the universe switched from slowing down to speeding up. That checks out. But this model makes a totally new prediction about a second transition, way off in the future, where the universe will actually shift back from accelerating to decelerating.
Okay, and this brings us to what is, without a doubt, the most critical section, putting these really fascinating predictions into their proper context. What does a study like this actually prove?
Let's be perfectly clear here. What this paper shows is a mathematically plausible scenario. It's a self-consistent model where dark energy could weaken. But what it does not show, and this is the key, is any observational proof that our actual universe behaves this way. This is one interesting idea floating in a sea of many competing theories.
And that brings us to our final section, letting us circle all the way back to where we started, answering the main question.
So, based purely on what's inside this research paper, not the headlines, not the hype, what can we responsibly say about this idea of a weakening dark energy?
All right, here are the takeaways. First, this paper gives us a compelling theoretical idea, not observational evidence. Second, the model has legs because it lines up with things we already know, like the universe's past switch to acceleration. And third, its new predictions, this idea of a weakening dark energy and a future deceleration, that's what makes it so intriguing. It is not a final answer. Think of it as one more fascinating clue for astronomers to test in the future.
So in the end, this paper doesn't close the book on dark energy. What it does is open up a new chapter by asking a really profound question. If a model like this turns out to be right, the ultimate fate of our universe might not be an endless accelerating expansion, but a gradual cosmic deceleration, less like a runaway train and more like a slow, gentle brake being applied. And that is a fascinating thought to end on. Thanks for joining me.